Hey y'all, this is an example for the standard normal curve, which is also working with normally distributed variables. So basically what we're doing is I'm showing you a problem where you're comparing the curve of a normally distributed variable with the standard normal curve and showing you how we get to the standard normal curve based on the data. So let me show you a quick example, and then hopefully that will help you as you work through the content. So the variable that we're going to be considering in this problem, we'll call it x, and x represents the run times from a race. I think it's a 10K, but I'm not sure, I can't remember. And the mean run time is 71 minutes. And the standard deviation is 9 minutes. So this is the information that has been given to us. And if I were to ask you to sketch the curve of x, then in the problem it would say this is normally distributed. So that's given to us also that it's normally distributed. So it's going to follow the shape of a bell curve. So you're going to sketch your bell curve. It doesn't have to be perfect, obviously, where the center of your bell curve is the mean. And then, actually, I think this is 61. It really doesn't matter, but. And then the standard deviation is 9. So each tick mark on your bell curve represents one more standard deviation. So one standard deviation, this represents 9, so it goes up to 70. 9 more is 79. 9 more is 88. And then we go below the mean, down 9, down 9, down 9. Is that right? I don't think that's right. Sorry about that. 34. Okay, so this is the sketch of a normal curve for a normally distributed variable with a mean of 61 and a standard deviation of 9. So these values here, this is one standard deviation above. So 70 minutes represents one standard deviation above the mean. 79 represents 2 standard deviations above the mean. 88 minutes, 3 standard deviations above the mean. And remember that we only go to 3 because by the empirical rule for normally distributed data, 3 standard deviations above or below the mean represents 99.7% of the observations. So it's about 100% of your data is going to be under this curve. And remember that the area under the curve adds up to 1. It can go no bigger than 1, which all ties back into the 100%, which is 99.7, not exactly 99.7, but you get my drift. So that's a curve of the variable x. Now, if they say standardize, write the standardized version of x, right? The standardized version of x, that goes back to a z-score. When we're talking about standardizing a variable, we're talking about a z-score. So it puts all of these scores on a level playing field. An example I gave in a previous video was if you were comparing two students to determine which one you want to admit to a college, and one student took the ACT and one student took the SAT, and the student who took the ACT made a 26 and the student who took the SAT made a, I don't know, 1800, you can't really compare those scores. If you don't know the nature of the ACT and the SAT, you'd be like, well, duh, a person who scored an 1800 is way better than a 26. but you don't know how to compare them until you put them on a level playing field. When you standardize them in respect to their means, their population means, and determine, oh, this student was this many standard deviations above the mean, and this student was this many standard deviations above the mean, then you can compare based on a standardized variable. So we standardize variables with a z-score, and that's the observation minus the mean over the standard deviation. So in this case, if we were to standardize the variable, we would have x minus the mean over the standard deviation. And that's all they want. It just wants the formula to standardize any runtime for this set of data. So we could plug in any value for x and figure out how it relates to the population mean. Part C is asking you to sketch the standard normal curve, or the curve of the standardized variable. Anytime you're going to be asked to sketch the standard normal curve, it's the same. The standard normal curve is always the same. You have your bell curve with the mean of 0 and a standard deviation of 1. And so this is a standard normal curve. The area under the curve is still 1. The curve is always above the axis. The mean is always 0. So this is the curve of if we were to standardize something. And this curve will always relate to the sketch of your distribution from part A, where we have a normally distributed variable and we sketch this graph, and it's going to relate to that curve, and I'll show you in a second how. So the next part is going to ask you to standardize some values, and then you'll see how it relates with the two curves. So this question is asking, and you'll see above I kind of sketched, it's a rough sketch of the two curves. We have the curve of the variable minutes, and then we have the z-curve, or the standard normal curve. And it's asking the area under the curve for, let's just say between 40 minutes and 70 minutes will be equal to the area under the curve for which two values on the z-curve. So in order to find which two values 40 and 70 correspond to on the z-curve, we have to find the z-score of each value. So it's saying, I'm just going to do a rough sketch here. I'm going to pick a different color, something lighter. It's wanting to find the area between 40 and 70. And we're wanting to figure out where that relates on the z-curve. Now I can kind of eyeball it and guess, maybe around here to here, but I need to be exact. I need to be precise. So I can find the actual z-score that corresponds to 40 and 70, and then know exactly where that is on my standard normal curve. So we're going to do a z-score. Oh, I should change my color so you can see it. For 40, and a z-score for 70. And I am pulling the formula from part B, where I standardized the variable using the z-score. So now you can figure out the decimal versions of those. And you should get, it would be equal to the area under the curve between negative 2.33 and 1, which you can see above my sketch is pretty close to that. That's going to be about here. Whoops, I want to do a different color. Colors are fun. From here to about, not about, it'd be 1 exactly there. And you can see that those areas represent the same. So we can find the area under the curve for the normally distributed variable as is, or we can standardize those variables and use the standard normal curve, which we know more about. We have more information about a standard normal curve than some random variable. And we have what is called z-tables, which you'll see in future lessons, which corresponds to areas under a curve. So I hope this helps clear some things up. If you have any questions, please let me know and I'll be happy to help. And that's all.